Thank you, Nancy, and welcome everybody. I want to give a talk that's not really a hand-waving talk, talking about a lot of generalities about energy and emission effects of these kinds of things. But so I want to have some technical content. At the same time, we will talk a bit about what's possible, what's likely to be coming in the future. Give you some perspective. It's easy for me to think of electric and hybrid vehicles as sort of a new emerging technology. That's not at all true, as you'll see here. We'll give some historical perspective on that as well. And even the wonderful cars that we've practiced with here at the University of Illinois, it always makes me feel old when I realize that was 15 years ago or so when we were doing those kinds of things, when we began doing them. But at the same time, it's gratifying to see that the industry is finally picking up on this stuff. So as we go along, I want to give a bit of a perspective because many of the advantages that emerged extremely early in the game remain valid, remain true, and remain motivators behind electrification of transportation as a whole. I want to give some perspective to sort of put some numbers on things to get you an idea of where things are going, and then spend a little bit of time on the arrangements of the modern hybrid vehicle, and then talk specifically about what happens on the environmental side, the energy side, as far as the meaning and the significant impacts, and some of the near-term developments we expect. And I'll put up a few slides of myths that actually came up at a major conference a couple of months ago about these kinds of systems. So yes, electric cars have been around for a long, long time. Why? Because they're clean, they're easy to use, they're easy to maintain, they're easy to control, the infrastructure is easy, everything about it is easy, they're relatively powerful, they're quite reliable. There's a 1914 Detroit electric car built by a venture of Henry Ford and Thomas Edison. And this one actually was photographed about 2 years ago in a driveway of a friend of mine in New Jersey, who has restored it, including the original batteries and so forth. The problem that it had then is the problem it has now. It doesn't go very far. It's a nice car, but you can't drive it around all day. Very limited range. Now, immediately at the initiation of automobiles, people figured out, well, you can solve that problem because you've got all these advantages of electric drives and electric vehicles, but it's really hard to get range. You're really stuck with batteries. The way to get around that is a hybrid because that way you can store the energy as a fuel and you can get a lot more range out of it. And sure enough, even by 1900, there were hybrid electric vehicles. This particular one was built by Ferdinand Porsche and shown at the Paris Auto Show in 1900. So, this is absolutely not a new technology, and indeed, some of the features of that car remain state-of-the-art today, go a little bit beyond what we see in production cars. Now, what happened? Okay, a lot of people have different ideas on what happened to electric vehicles. Some people will tell you it's the electric starter and Kettering and other things. Well, in fact, there were two things that happened. Number one really was Henry Ford, if you will, doing it to himself in the sense of saying, I want to make vehicles for mass market that have all the features that people want, that everybody's going to want to buy. And sure enough, in 1909, as we had cars that were intended to appeal to a mass market with I haven't tried to do the inflation adjustment on that list price, but it's certainly an intriguing number, right? And indeed, at the time, gasoline was actually considered a waste product. It was extremely cheap. In an energy sense, it remains somewhat cheap, although we'll see relative values a little bit later on. So mass production, getting costs down, trying to appeal to a mass market, lots of range, be able to go and do a wide variety of things. By about 1920, the market size for gasoline-driven cars had overtaken that on electric vehicles. And certainly by 1930, electric vehicles essentially were gone, dead and gone. Reliability has been improving, so if you will, gasoline cars have sort of begun to approach what you can do with an electric vehicle, with still that range issue being there. On the other hand, we had a very long hiatus for 30 or 40 years in which there wasn't a lot of technology change. Now there's been a great deal, and that, of course, is why we're seeing this come back again. Hybrid vehicles themselves began to revive in the 1970s. There were some very nice demonstration projects. And finally, in the 1980s, we got to some serious new electronics applications that made a big difference. The General Motors Sun Racer was perhaps the first classic one there, and I don't actually have a picture of that one. Ultimately going to the General Motors Electric Vehicle 1 EV1 project in about the year 2000. The electronics have been mature now for about 12 to 15 years. When we were doing projects about 15 years ago, there was still an evolution going on. By the time we, I won't say wrapped it up, but by this time we went through a couple of generations, we were actually working with pretty much commercial off-the-shelf hardware that can do the job. Batteries sort of continue to emerge. Nickel metal hydride batteries matured enough in the late 90s that they became the basis for the modern hybrid electric vehicle. And the lithium-ion batteries that we have in our laptop computers have now gotten to the point where that Tesla Roadster down there in the lower right can use those kinds of batteries and actually get very good performance out of them. So the electronics revolution certainly caught up with this problem in the 1990s. Batteries, if you will, have been moping along and have gotten sort of where they need to be. And the classic example, indeed, was that 2000 General Motors EV1. I don't want to talk about its history and all the things that happened to it. It's a subject of movies and books and other things, some of which is true and some of which isn't. I can tell you there was a very frustrated engineering team in Troy, Michigan, that was very sad to see that project beginning to go away, and now finally some of the folks up there are seeing the light, as it were, in terms of what could have been done if there had been more focus on it. But still limited range. Okay, that car has a battery full range of about 50 to 70 miles, depending on how it's driven. Okay, that's not bad. At the same time, the minivan I have parked out in the circle drive, the fuel light comes on when it's got 50 miles of range left. It starts yelling at me to go get more energy. So, you know, in terms of a cultural shift here, you have to think of that car as driving around on empty all the time. Okay? And some people got used to that. You know, it was easy for them to plan out the trips and understand what they were doing. Others felt like they were always worried about where am I going to be, where's a place I can connect to, how can I get this vehicle charged. You know, it places a damper on what otherwise is a very high performance vehicle. Now, that said, hybrid electric vehicles have been around for a long time. There's one, okay? And certainly in the very large transportation industry, when you're talking about ships and submarines and locomotives and large mining vehicles, they've been hybrid electric for 2 generations. It's simply the only way to do very large-scale power management. So in a vehicle like that one, that diesel engine, there's a very large diesel engine, indeed, that drives a generator, generates electricity, which then is controlled down to electric motors that are hanging underneath on the trucks that actually drive the thing. And when it needs to brake, the motors turn into brakes, send the energy back actually to a set of massive resistors in the back with big fans that blow the heat out. You know, it is a hybrid electric vehicle, and it's been around. It's been that way for a long time. And there are good reasons for that. Namely, when you start putting something like an electric motor in a car, you get lots of flexibility, lots of performance, lots of reliability, and relatively low cost. So here's a little motor. I gave it for scale there. That's one that actually we put into a Ford Escort. Its nameplate rating, it says 10 horsepower when you go buy it from the motor manufacturer, and it's about a $200 motor. When you start to look at the way automotive people rate things, its automotive rating is actually close to 100 horsepower. And it can take far more abuse than a gasoline engine, but it's perfectly adequate to operate that vehicle. And indeed, if you don't use it right, it's hard to keep the tires on the street. So it's got a pretty good amount of performance. So performance is not a problem. The motor is easy. The problem, again, range. It's always range. It's always been about range. Probably always will be about range. You've got to store energy that you can deliver to that motor to carry the car along, and it's got to be self-contained and carry it itself. So let's look at that quickly, and I am going to put some numbers on here just to give you some relative perspective. How can I store energy? There are electrical devices, capacitors, inductors that you can put energy into. There are flywheels and springs. You know, I can hang a great big rock up on a rope and store energy with a gravity method. I can shove a lot of air into a compressed air tank. I can use batteries, or I can use a hydrocarbon liquid of some sort. And the question is, you know, I want to put this in a car, okay? So the thing I'm most interested in is how much weight, how much mass of material am I going to need to store the energy I want to carry around with me. There's also a little bit of an issue with size when we talk about something, for example, like hydrogen. It's very light, and I'm not even going to address that in this talk. But you know, if I need a whole stadium worth of volume to hold it in, that's not going to help me much either. But another issue is how fast can I deliver that energy? Can I make that vehicle accelerate? Can I do some of the other kinds of things that I need to do? So let's get some perspective. As I say, I want to list some numbers. Metric equivalents, just for comparison. Lead-acid batteries, we're all familiar with that. Everybody's got one in their car. 100 kilojoules per kilogram, whatever that means. Lithium-ion batteries, better by about a factor of 6. That's probably the important thing here. You can take a scuba tank and jam a whole bunch of air into it. That's actually worse than a battery, and it doesn't take into account the weight of the tank, so that's a problem. Little electronic gizmos that we use, capacitors and some other emerging things, not remotely close to batteries. I have a wonderful brochure from a very expensive, high-end manufacturer of a flywheel system, and down in the bottom it says, as good as batteries. Okay, so the interesting thing is after all these years and all the methods and all the things that people talk about, batteries, although people like me hate them, they're a really good way to store energy when you want to carry around something that's portable. And, of course, many of us have little portable devices that run on batteries. But liquid fuel, gasoline, okay, 43,000 versus 100 for lead acid, 600 for lithium ion. It's not even close, okay? It's a complete no-brainer. Now, the only problem is I can't get all of that energy out. I've got to burn the fuel and run through a thermal process, which typically is going to only give me about a third or maybe even less of what's actually in the fuel coming out to do useful mechanical work. But even with that, right, even if I give up, you know, 3/4 of that or 90% of it, I'm still far better off than I am with the other technologies. And that's an issue, right? So here's an electric vehicle demonstrator. It's got about, 600 pounds of lead-acid batteries in it, and that massive battery pack gives me about 1 gallon of gasoline worth in that car. Any more than that, and of course the vehicle just becomes a battery carrier. It doesn't really carry passengers anymore or goods. It just carries batteries around. Not a real good trade-off. So it's really hard to beat gasoline or methanol or ethanol or some liquid hydrocarbon as a way to store energy. And that really is what hybrid vehicles are all about, is trying to put those things together somehow. Rate's also a problem. Okay, typical thing, right? And this actually isn't that aggressive. Okay, put 15 gallons into a gas tank in 5 minutes. That can be translated now into a rate of exchange of energy, right? And I won't put the numbers on it, but basically we can take about half of the campus, and you know that's the kind of rate that we're talking about. So if I tried to set up an electric vehicle filling station that could fill 6 cars to that equivalent amount of energy in 5 minutes, okay, it would consume more electricity than all of Champaign-Urbana, essentially. Okay? So it's really out of the question. And the batteries really can't take it anyway, so it doesn't work so well. Now, people, I think, have put weird spins on this. They said, you know, nobody's going to want an electric car because they're going to have trouble going and refueling it. Well, I don't know. I would rather park my car in my garage and plug it in. Who cares? Okay, I'll come back in the morning. That's what I do with my cell phone and my laptop. I don't really expect to plug them in and 2 minutes later have them totally full and ready to go. It's a totally different world, and indeed there's a lot of disparity in terms of people talking about the different things. By the way, there on the lower left is a plug-in hybrid electric vehicle, which supposedly is a wonderful new technology. That car was built in 1996. The other one was like the 2, is built 3 years sooner than that, but you know, there's nothing new under the sun in many ways, I suppose. Okay, a few minutes about the modern hybrid. There are a lot of different architectures that are used. They really are motivated by different efficiency and emissions trade-offs. And you make a lot of decisions in different ways. And I can see this in different things that have come on the market. So for example, it's possible to take a hybrid electric vehicle which has an engine, some sort of electric generator, various controls, one motor, maybe ultimately up to 4, one for each wheel, I suppose, fuel tank for storage, you know, and trade these different elements off to achieve different end results. So for example, the Honda Insight that was introduced in the United States in June 2000 really was engineered for highest possible fuel economy. And when you look at it very carefully, you see the issues. It's a 2-seater car, very limited cargo space, a lot of aluminum in it to get the weight down, a lot of compromises to keep the engine running pretty minimally. It gets extremely good gas mileage. The Toyota Prius, which came out in this country about 3 months later than that, was in fact engineered for minimum possible tailpipe emissions. And I think most of the people who purchased them at the time didn't really understand that. But it's not optimized for best gas mileage, although its gas mileage is pretty good. It is optimized for really, really low emissions, and in fact achieve that quite successfully. And there are different ways that people can do things too, and we see that now reflected, I'll come back to this, in some of the near-term developments. A lot of discussion about, you know, is there sort of a generic hybrid design, or, you know, should I have one for a commuter car? Should I have one for long distance? What would I use for this function? What would I use for that function? And indeed, it's a problem because they don't match up against things that well. The general types are two things we call series and parallel. There are different ways to define those, but basically in a series hybrid, the energy is brought together electrically. So it's sort of an electric car with a little engine generator set in it. And parallel means the energy is brought together mechanically. So that electric motors and engines tend to hang on the axle and fancy transmissions and other things. Fundamentally quite different. Most of the things that are on the market now are basically parallel hybrids. So this one is a little bit clearer, I think, sort of a representation of one of the Honda vehicles with a gasoline engine, a transmission, and basically a small motor generator sort of linked into that system to give it some capability. The ultimate is what's there on the left, which is what we sometimes call an integrated starter alternator design. So this actually has, this engine basically has an electric motor built into its flywheel. And what that does in this case is it allows it to do some interesting things like recover energy when I brake. It allows me to turn the engine on and off at a stoplight really conveniently without really noticing much of an effect. I even saw one version in which they actively controlled the electric motor to cancel out torque vibration and basically make the flywheel as if it were bigger. And the engine runs really, really quiet in that car. It's a very impressive technology demonstration that I haven't seen in the market as yet. Toyota, Ford, Nissan use something they call a dual hybrid because they have modes that sort of look like these different things, although technically we would call them a parallel hybrid. So what happens is in the Toyota car there's a battery pack, a lot of electronics, a motor, an engine, a generator, and then this special transmission that allows me to bring these things together. And because of the nature of the transmission, they can sort of be mixed and matched. So at times the generator operates, at other times it doesn't. And the things come together then to give a range of functions. The Toyota version is something that's called a mild hybrid that looks a little bit more like the one we were looking at a moment ago. Basically, the idea is to allow the engine to start and stop a lot and get better control over efficiency in particular through a process like that. Now, I don't want to get technical, but a lot of people who work in this area like to say that their vehicles have continuously variable transmissions in them. In fact, the transmissions in those cars have no variation at all. They're all single speed, fixed. But they have multiple parts so that basically you can bring the energy in from different directions and sort of achieve the effect you would have as if it were variable, but it's not. So I don't, that name came out of somebody in marketing instead of somebody in engineering, I think. As you know, there's some in production. The original version of the Insight, again, a two-seater. The original version of the Prius, and those now have been around for a long time. And I remember when they first came out, people said, you know, they're going to have problems with batteries. Batteries are expensive to replace, you know, so on and so on. The car at the bottom there. You bet. And I use them constantly and charge them a lot. Okay, I don't know how much we lost, and maybe it doesn't matter, but is it coming through now? Okay, good, thank you. All right, others too. Ford certainly joined the fray early on. Lexus is another Toyota version, and many of these do have slightly different trade-offs. What we've seen, for example, more recently is some of the cars from various manufacturers, actually not these, that try to say, okay, we're going to make a hybrid platform, and we've got the performance of the engine, we've got the performance of the electric motor, we'll add them together and give the vehicle a little bit more performance and a little bit better gas mileage and still somewhat better emissions, you know, trying to appeal to broader markets. That's succeeded only to a limited degree. I remember someone who bought an early Honda Civic hybrid and said, well, I'm getting 15% better gas mileage. You know, why? What's the point? I paid more for this car. It's really not showing me dramatic change. They had made a bit of a trade-off to put more into performance. You know, a lot of people aren't that concerned with it. So there's still a lot of marketing that goes on here to try and understand what we can do with these different things. Okay, I want to get into the energy and emission stuff and get some of the motivation. Yeah?
All the hybrids you showed us, all of their energy comes from gasoline.
Absolutely, absolutely.
Now you're introducing another stage, which is an inefficiency going from the gasoline. So just can you mention the factors that more than make up for that extra thing? What are those?
Yeah, we'll actually begin talking about that right here because I want to bring that in. The point's well taken. All hybrids on the market today get all their primary energy from the fuel. Okay, they have an electric element in the drivetrain. They have a battery pack, but the energy ultimately comes from the fuel tank. Okay, there's no plug-in hybrids on the market just yet, at least in any mass market sense in this country. But you do gain in energy efficiency, and we'll come back to why that is. They actually are significantly more efficient. So yeah, I need to touch on that here, and I will in a couple of slides or so. Okay, so what are the motivations? Now, I want to go backwards a little bit and think about purely electric for a moment, and then we'll come back to the hybrid. Okay, why electric vehicles today in our current context? I mean, we still have all the things about clean and easy to maintain, and they work well, and they've got a lot of performance. But energy flexibility certainly becomes a significant issue. You know, I can't run a conventional car on coal or nuclear power or hydroelectric power. You know, an electric car I can run on whatever is being used as the regional energy source. Efficiency certainly is a factor. Tailpipe emissions per se, and we'll talk about this in more detail. Clean, quiet cars. This actually, there's a detail here that I like as an anecdote that somehow has popped back up again. I'm not sure why. 15 years ago, when General Motors and others were looking at electric vehicles, they said, we want them absolutely quiet. That's one of our things. We want it to be an absolutely quiet car. You know, that's going to be one of the features. We'll sell that. People will like that. Okay. First day we took a hybrid car around campus, we had it set up to be absolutely quiet. And there were 6 near misses around the first block. Okay. Now things are worse now, right? Because everybody's got an iPod. Okay. So I'm not sure it would matter. We went back in the lab and we adjusted it so it would make some noise. Okay. And all that problem went away. Today we're going back to that same issue. You know, I talked to somebody from Tesla a few weeks ago. He said, no, I want my car to be absolutely quiet. You know, he said, yeah, I'll have problems with the blind people, but I have problems already with all the people with the iPods anyway. So, you know, what difference does it make? I have to be more alert. I think he's crazy. But, and Toyota and Nissan are now struggling. You know, do we put noise into our cars? Well, to me, it's a no-brainer. The car's got to make enough sound that the driver knows it's working and that somebody's going to look around and see it coming, and you don't have to make it objectionable. So we're going to see an interesting way in which that plays out. You know, I like the noise that the car makes, but we have to be very careful to make sure it's not objectionable. Emissions, right? They could be eliminated, or at least they're moved to a central plant. We'll come back to that a little bit more here in a moment. Okay, hybrids. Why hybrids, right? Really here I'm trying to overcome that range issue. Okay, I'm trying to get more energy into the vehicle, and I'm trying to overcome that the rate issue as well, make it easy to refuel it. But to the question, it's fairly well established now that a good hybrid design, for reasons I'll go through here in a moment, can in fact double the fuel economy versus basically an equivalent car of the same nature. So if I take you know, a Toyota Camry, rebuild it into a Toyota Prius, and do my work carefully, I should be able to get about double the fuel economy. In principle, we've looked at some other things. You look at weight trade-offs and some really, really careful algorithms about control. It looks like maybe it's possible to get up to about triple. So that the old CAFE standard of 27 miles per gallon becomes 54 or, you know, about 80, 81. That's plausible, but it's hard. Yeah. Interesting question, okay? He asked, what about city versus highway? A properly designed hybrid car should be far more efficient in city driving than in highway driving. Why? Because you lose less energy driving around at a low speed. Okay? It just doesn't take as much power. And in a hybrid, I can actually make the trade-off because I don't have as much overhead as I do in a gasoline vehicle. So that's sort of my first litmus test. You know, is this car a real hybrid? Then its city mileage should be higher than its highway mileage. Okay? And we don't see too many on the market today that have that characteristic, but in some sense they should. Although I have to tell you, you know, the last a couple of years ago when I went up to Chicago for a meeting and I was stuck in traffic on the Dan Ryan, it really felt good to be in a hybrid, having the engine turn off. I'm sitting there getting infinite miles to the gallon. The people next to me are all cussing at the fuel they're consuming, whatever, you know. Takes a little bit of the edge off of things to get that extreme of mileage in stop-and-go driving, right? So infinite mileage and stop-and-go driving. It's a pretty good trade-off. In fact, it's possible to get an overall efficiency that's not so different from a true thermal electrical plant. Because if you think about it, yes, I've got that primary fuel source, but I can, drive that engine in a way that's not so different from setting up a big coal-fired power plant. And indeed, the overall efficiency can be extremely good. Now, I want to look at that in more detail, because this is also efficiency. But how does a hybrid electric vehicle reduce emissions? There's at least 5 things up here. These also impact efficiency. Number 1, I don't need as big an engine, because I don't need the engine to do all the work when I want lots of power for short periods of time, and we'll come back to that a little bit as well. 2, I can indeed turn the engine off when I don't need it. 3, and this becomes maybe more important, I can choose how to operate the engine, because now whatever the driver is asking for, I have multiple ways to address that need. I don't have to address them purely with the engine. So I can make trade-offs either in the direction of emissions or efficiency, trying to improve things. Number 4, and this one is extremely important, modern gasoline-driven cars have most of their tailpipe emissions in the first few moments when they're first started up, because the catalytic converter and the emissions management system aren't warmed up, and they really don't do anything. You've got essentially raw fuel coming out of the tailpipe. In a properly designed hybrid or electric car, I've got this battery pack, and I should be able to use that, for example, to preheat things. In the Prius, they do it a little bit differently. They have sort of a mechanical box that tends to confine the emissions for a short period of time as everything warms up. So, for example, my first generation Prius, I said it was designed for minimum emissions, which is true. But when you first operate it, you find out that the car's algorithms are all about getting that engine warmed up. That's what they are doing for the first several minutes. It's all about that. The passenger, uncomfortable, performance, everything else. Let's get that engine warmed up. Yeah.
This seems strange if it were a big issue for the ordinary battery in an ordinary car. The number of watt hours needed in the catalytic converter isn't a lot of mass.
Right,
It's
right.
also metal, so the heat capacity is minimal. This could easily be a non-problem for the ordinary vehicle.
Interesting point. I mean, that's true, and there have been some inventive things about, catalytic preheaters and other things that would use, say, the existing electricity in the car. So yeah, potentially. A lead acid, the standard lead acid battery in a car doesn't lend itself to that very well. That kind of thing would tend to kill its life, but there's no problem in principle. And indeed, we have seen a little bit of that. I mean, as the emission standards have gone up in California, for instance, this is one of the kinds of solutions that some of the manufacturers are looking at. How do I either provide thermal mass in a catalytic converter that will store more heat, so that when the car is parked for a while, it won't cool off as fast, or provide some sort of a preheat mechanism or a recirculator that tends to get heat into it much more quickly. So yes, some of those technologies are being explored. There may be easier ways to do it. That's fair. Break-in energy can be recovered. I deliberately put that last because although many people hear about that a lot, it depends, on whether that's a major factor or not. When I'm driving on the highway, I'm not going to get any energy back out of my brakes. That's obvious, right? And when I'm totally in stop-and-go driving, then of course I want to recover that. But driving around Champaign-Urbana, the impact on energy is, it's a mixed bag. Depends on the traffic and the patterns and the stoplights and everything else, and it may not be that big a deal. I think people have said that in conventional city driving, it could be about 30% of energy being recovered, which is significant, but not as significant as some of the others, actually. Some other interesting things you can do, actually, is use engines and engine methods and cycles, thermal cycles, that maybe aren't so good for operating a vehicle. Diesel-electric locomotives are efficient because they use massive diesel engines, and you can make them efficient If you don't mess with them too much and you got lots and lots of space, you run them slowly. Very hard to do that in an automobile. We typically use auto cycle engines. The Toyota cars now use what's called an Atkinson cycle, which is a little bit more efficient, but doesn't give as good performance. A hybrid car, I don't care. Okay, I can make that trade-off because I got an electric motor to add in the extra short-term performance I need. Possible in principle to use a turbine, although they don't scale down very well, so it's hard to make a small, efficient turbine. Nevertheless, Volvo, for example, did demonstrate a turbine-based hybrid electric vehicle at one time. And in principle, that could be a lot more efficient. Okay, net result, the Prius, the first generation Prius got about a 90% reduction in tailpipe emissions with basically the same performance as an equivalent Toyota car. The biggest improvements are in hydrocarbons, carbon monoxide. I think the first generation Prius is rated for lifetime hydrocarbons over 100,000 miles, such that if I were to spill 1 cup of gasoline on the ground while I refuel it, I would kill its lifetime capabilities. So it's extremely good for hydrocarbons, and usually it's somebody messing up that causes the problems on top of that. You do at least have some possibility of at least a range in which you operate only on electric, quote unquote, with zero emissions. Again, from a system level, we have to think about where those things are getting moved to. Okay, right? So this is an old argument people used to make. I have an electric vehicle, it just moves the emissions to a power plant. Well, that's a good thing for 2 major reasons. Number one, I now have this large central infrastructure where I can do a lot more optimization in how I manage an emission stack. And it's well established that that has very significant benefits and does make a huge difference. And of course, I have the resource flexibility. But there are some differential impacts there that we need to look at. And you do get overall higher system efficiency. So even though I can build a hybrid car that begins to approach a power plant, if I'm using the electric power, storing it in a battery and driving the car around, that stack up is still more favorable, at least to a degree. All right, some slightly more specific things here. The true emission impacts depend, of course, on the generation mix in a region. And the results that I have are sort of for the average U.S. mix. So, for example, hydrocarbon emissions with an purely electric car moving its emissions to the power plant, I think the numbers I've seen are hydrocarbon emissions down around 95%. Carbon monoxide, even more so. It's very dramatic. NOx, much easier to control at a power plant than in an automobile. This is a hard one to control on a small transportation platform, so there's a big impact there. Carbon dioxide, of course, is only reduced in proportion to the energy use reduction, basically. So to the extent that the vehicle is more efficient overall, it can reduce carbon dioxide emission, otherwise not so much of an effect. So that effect is a little bit more modest, right? Where it doesn't have so much effect, at least in this part of the country, is on sulfur oxides. Because, of course, as soon as I start running an electric car, that means here in Champaign-Urbana, it's running on nuclear and coal. And coal means sulfur emissions. The studies I've seen do show a small net reduction, but not a large one. So there's some impact there, a little bit of a differential on these different kinds of emissions, right? The carbon impact then is a little bit more indirect, and we'll have to look more closely at that. But I want to explore energy a bit. One of the key points is not merely energy resource flexibility, which is very important, but also energy time flexibility. If I'm driving an electric car around and I want to recharge it now, that's one thing. But if I plug it in overnight and I want it to be full in the morning, I really don't care how the utility achieves that. As long as you give me this much energy by 7 a.m. tomorrow, how you do it is your problem. Okay? And that is a vast difference compared to the way most of the electric power system runs. And that kind of time flexibility has some really very large potential advantages. But to give you an example here, the top chart there is a price plot from an August day taken at one of the Ameren IP test sites. It's price, but in this context, it translates actually into demand. Okay, and there's two things I want you to notice there. Maybe you can read the values, maybe not. This is a wholesale price. It's showing the peak price about 2 o'clock in the afternoon with a value of about 8 cents a kilowatt hour. And it's showing a price at about 4 o'clock in the morning at less than 2 cents a kilowatt hour. Okay, I want you to keep that in mind as we come back. The plot on the bottom is an actual measured production trace from a solar array on the same day at the same times. And you see it's, solar's fairly predictable. We know what the sun's going to do, right? Clouds are less so, so you see little spikes there as it kind of goes up and down. But you notice it doesn't quite match. You see it's to the left, shifted to the left relative to the other one. So from the power company standpoint, solar's nice because it produces power during the day when we need it, but it's not so nice because it doesn't quite coincide with the peak. What am I going to do at 2, 3, 4 o'clock in the afternoon when people are using lots of power? My solar is sort of fading away. How do I mix and match and make up the difference? And that becomes more problematic, actually, as we add more wind and solar resources. Solar, again, predictable, but certainly a lot of randomness on top of it. Wind, much less predictable, quite a bit of randomness on top of it. And this is difficult in a conventional way of operating a power grid, because in the power grid, energy has to match what's being used moment by moment. I put second by second. It's probably more like millisecond by millisecond. Basically, whatever's going out has to come in. We have to have energy conserved and balanced, in real time, all the time. And if there is a cloud that goes over a big solar panel, and suddenly I get this big spike going down, what do we do? We got to come up with that energy someplace. The problem right now, and it's a little bit overstated, but there are some people who will say, for every extra solar panel that we put into the system, we've got to have an equivalent amount of coal-fired generation available to make up for it, so that when it's jumping up and down, we have a resource that can make up this difference. Okay, and I think the key point I'm trying to get at is if I had something with time flexibility, like a big battery pack, I can make this problem go away. Because now I can say, okay, fine, the resource went way down for a moment. Okay, we won't charge batteries for that moment. We'll wait for a moment or two and then come back again. And that is going to be really very key as we bring these more random resources into the energy mix. So getting that large-scale flexibility and being able to adjust battery charging dynamically to make it match with the load. Okay, now I've moved the problem into another arena. We have a communications challenge. We have a control challenge. How do I make these things interact? And of course, as a customer, right, they want to know, is my battery pack going to be full at this particular point in time? So now the power company's got to deliver me a certain amount of energy over some amount of time, even though they're allowed to sort of pick and choose the details of how to do it. So electric vehicles and plug-in type hybrids become a possible storage resource, and the benefits are very, very significant. And as long as we can meet those requirements and keep the people happy with the energy that's being delivered to them, makes a huge difference. Now, the other possibility is simply to shift load into the nighttime hours. Okay, and I think there's a little bit more on the next slide here. We were looking at a graph a few moments ago that showed a ratio of night to day of somewhere between 4 and 5 to 1. Okay, more typical in the United States is about 6 to 1. There are times, typically in February, in Champaign County, when electricity at 3 o'clock in the morning is free. I've seen a couple of times when the price was actually negative. Okay, they wanted to pay somebody to use it so they don't have to turn the dials down on the Clinton nuclear plant. I mean, that's the bottom line. You don't want to mess with that great big resource. It's supposed to sit there and run constantly all the time. Sometimes that'll happen during a holiday as well. Yeah, but less, what happens in the winter is they're playing with maintenance issues and there's a different mix of the generation. Sometimes in the summer they get lucky, and suddenly everybody's home for the weekend and you see these price things. Okay, what's the easiest thing to do? Have people charge electric vehicles at night. Okay, so now, well, in fact, a friend of mine who has an electric car in Northern California, most expensive electricity in that state, very, very expensive electricity. He has a special electric vehicle rate, and if he charges at the right times, his charging price is 2 cents a kilowatt hour. Okay, and they're happy to give it to him. They're making money. It's allowing them to keep some of the plants up to snuff. Studies have been done that say that if 10% of the people in the United States had electric cars, provided they charged them at night, there would be absolutely zero impact on the grid. Actually, it would probably be positive because we could take more of the plants now that are having to go up and down day by day and run them more constantly, better emissions, better efficiency, better economics. So we actually improve the power system by adding more electric vehicles rather than stressing it. Okay, I want to look at some of the numbers here, give some power requirements, and then we want to wrap up with trends because I want to put this a little bit in context because the way we buy cars and the needs we have are rather different. Okay, typical sedan, right? I go to the automobile store and the guy there is trying to sell me this wonderful name brand car with a 250 horsepower engine and look at all the wonderful things it will do. Well, when I'm driving it on the freeway at standard speed, it's using about 20 horsepower. And if I'm driving it aggressively up a freeway in the west, 50, 60 horsepower. If I really want to go 95 miles an hour, not a big deal. Maybe if I'm trying to get onto a freeway, I'll get up into the mid-hundreds range. The chances of that car ever putting out 250 horsepower are very, very low. It's got an engine size for that. There's a problem here, right? When we do a hybrid or electric design, it's much easier to make those trade-offs. It's easy for me to make an electric motor that puts out 20 horsepower continuously here on a level road, 50 or 60 horsepower for a few minutes at a time, and 150 or 200 horsepower for a few seconds. Okay? Not a very difficult trade-off. I don't have to oversize things dramatically to do that. And I don't have to sacrifice efficiency. So what happens here, that the engine in a typical car is designed to be extremely efficient at very high power levels and so forth. So yeah, if I'm driving at 100 miles an hour, that's a really efficient car. I'm consuming lots of extra power to move through the air, but that's a different issue. At 20 horsepower, at 65 miles an hour, it's not so efficient. That's where the mileage is measured, but it's really very hard to optimize it that way. And we play all kinds of games with transmissions and other things to do it. Electric, not nearly as big a deal. Designing a car that will be extremely efficient in all those different configurations is relatively straightforward. Okay, so when we go to a hybrid now, I can choose the engine to deliver the average needs. So now suddenly a sedan like that could have a 60 horsepower engine in it and the electric motor to make up the difference. And the driver will never know. If they want to accelerate onto a freeway at full speed, no problem. It'll give them all the performance they're ever used to. Really hard to advertise and say, hey, I got this wonderful 60 horsepower car. Right? Nobody wants it. Okay? Even though its equivalent is probably 300 horsepower, but you can't, we're not in a position where we can lie about all those numbers yet. So that'll come. I've already seen that in small appliances. If you don't believe me, look at the horsepower in a vacuum cleaner, which the last one I bought, I don't know what it said. It said something like 8 horsepower. You cannot plug an 8-horsepower motor into an outlet in a house. Okay, it will blow the circuit breaker immediately. That's how they came up with that number. I have no idea, and it doesn't mean anything. Okay, costs. Costs are an issue. People ask about this a fair amount. Gasoline, I just chose an easy number here, $2.40 a gallon, 30 miles per gallon. So energy cost of that car is 8 cents a mile. Okay, whatever. Sounds relatively cheap. Electricity here in Champaign-Urbana is about 12 cents a kilowatt hour. Reasonable electric vehicle design, about 200 watt hours per mile. That's 2.4 cents per mile. Okay? Well, that's if I charge it at 2 o'clock in the afternoon when everybody's using power. If I charge it at night, it's factor 6, cheaper than that. Okay? And now the energy is almost free, right? So it's kind of a no-brainer. From an energy cost perspective, electric vehicles, plug-in vehicles, it's crazy. Anybody who had a plug-in hybrid vehicle is going to do their best to avoid ever going to a gas station again, right? They're going to plug it in, for crying out loud. Interesting sidelight. Today, solar electricity is very expensive, okay? 2.5 times, roughly, conventional. But when I put it up against the numbers we just looked at, 30 cents a kilowatt hour, 2.5 times 24, what is that? 6 cents a mile? It's still cheaper than gasoline. So we talk about solar power being expensive, okay? Gasoline's expensive. Solar power is cheap. And of course, in the United States, gasoline is cheap, right? In Turkey, I think in Istanbul right now, it's probably about $11 a gallon. And of course, what do you see in Istanbul? You see traffic jams and pollution and so forth. You would think everybody quit driving. Solar power, of course, is getting dramatically cheaper. This is from a manufacturer from about 2 years ago. Yes, it is on that trend. So, we're seeing here in the next 5 years the cost dropping roughly in half. It begins to make a lot of sense to have solar panels on a roof, an electric car in a garage, and charge the things together. Okay? And indeed, photovoltaic power gives you about 20% of that energy. It does matter. I don't want to talk about the comparison to biofuel, although there are some numbers there. What I want to do is jump into some of the myth things, and I'm even going to skip over this. Basically, the bottom line is that, how do you charge a car? Can you interface to a house? And the answer is it's really not that big a deal. We already talked about that a little bit. What I wanted to do is jump to some of these myths. Okay? I hear these over and over. I've heard them from industry people who are experts. Okay? That first one's a direct quote, right? Nobody wants to buy a car just for commuting. There was a time when they were saying, fine, sell electric vehicles, it's commuter cars. And they say, well, nobody will buy them. Well, pardon me? That was a year ago November, so about 13 months ago. Okay? That's very much the attitude in the industry. Now, all my neighbors, probably most of yours, have a car that they've purchased that they pretty much use for commuting. Right? So I don't know why the folks in Detroit think that people won't buy commuter cars. They already have them. This is one of my favorites. They're saying, well, we need lots more electrical infrastructure. How are we going to get it? Where are we going to put it? So on and so on. Meanwhile, in places like Minneapolis, they have outlets on parking meters, right? It's not that big a deal. If you have an outlet in your garage and a plug-in hybrid car in your garage and an extension cord, you're in pretty good shape. Okay? Wow. That turns out to be a fairly detailed question. Probably the best answer is because in the early days when they were putting in hybrids, they were very concerned about battery life. And anything anything that they could do internally to manage the battery system was really important to them because that was what was going to give the life. And Toyota, by the way, has been very successful with that. So that strategy has really paid off. But as soon as you go to a plug-in, now the customer is more managing the behavior of the batteries. It's a lot harder to manage their life characteristics. And we've kind of been waiting for the lithium batteries to catch up enough where they can handle, that somewhat less controlled environment and still work out fairly well. So that's probably the most important reason. There's some others as well.
I'm sure you know these numbers off the top of your head, but there is a nasty fact about cost. Doesn't the Argonne group say that it's roughly $500 per kilowatt hour right now, with the goal of pushing it down to $250?
Yeah, lithium-ion batteries are fundamentally expensive.
Bucks times 20 kilowatt hours.
Right.
Storage is $10,000.
Exactly.
On batteries, and you don't even have the wheels or the
Yeah. Well, and that of course is not related to whether it's plug-in or not, but the issue there becomes how can I come up with the right business model that helps me amortize that? Because obviously if the energy is more or less free, then the difference between the cost of the gasoline and the cost of the electricity in effect is being amortized in the batteries.
And similarly, all your discussion about the battery as a storage vehicle, again, at $500 per kilowatt hour, that's pretty expensive storage.
Not so expensive compared to a lot of other alternatives that the industry looks at. So right now the utility industry is trying to look at storage. How do I mitigate wind and so forth? Do I build big underground caverns to put compressed air into and so forth? And $500 a kilowatt hour doesn't quite look so bad when you start to compare it to some of those big projects. But the point's well taken. I mean, I can think of those $10,000 as prepaid fuel. How do I make that work? And of course, right now the industry is saying, we're not going to worry about it. We'll just sell them to the people who are willing to prepay for the fuel. Tesla Roadster list price is $109,000. Okay, they can't make them fast enough. The Chevy Volt, when it comes out, I think its list will be $40,000. I don't think they'll have any trouble. But there are other people saying, let's lease the battery and move the business model somewhere else, and somebody else is making the money on that. I think that's still wide open, how to work that best. But for example, in my Prius, right, expensive nickel metal hydride pack, but it's a part that never needs any service. So again, it's like a prepaid cost that effectively never has to hit me. So, I have to worry about what happens with a big ticket maintenance item every 10 years versus a more modest one that's every 2 or 3 years. So it's a different way of doing things, and it doesn't quite fit as well with a lot of things. Yeah.
I think a major concern for consumers is dependability. I mean, the Chevy Volt is essentially like a $40,000 Cavalier, if I understand correctly. I don't know too many people that are really willing to spend money on a Cavalier. They just don't last long enough. So they have the technology to drive a long way, but they don't have the guarantee to back it up. It's going to be there long enough for you to actually recoup your money.
Well, yeah, and part of that is a business model. I mean, if the Chevrolet Volt has been engineered to last 20 years, I mean, it's not a big problem in that kind of a vehicle to do that. Are they willing to put out and match that up against the warranty and so forth? That remains to be seen, right? So there's a big gulf between what you can build technologically and what you've set up in the market and the business model. Absolutely. But to your point, the small Chevrolet SUV is in fact that same vehicle with a slightly different body on it, and it's $40,000. So, somebody is paying a lot extra for a fairly modest increase. So, there'll be plenty of people. They're not going to have any trouble selling them. But yes, I don't want to get too cynical about it. But your point's well taken. Yeah.
Ameren announced this weekend they're going to be putting in smart grid parts of St. Louis and Springfield.
Right.
Is this part of the equation of that? Are they planning on a certain percentage of nighttime storage of plug-in hybrids type thing as they're doing this, or is?
Yes and no. Certainly the smart meter things that are coming along will be necessary. In other words, I can't get a nighttime rate on an electric vehicle unless I've got meters that have all the time information and everything else in them. So it's sort of a fundamental first step. I don't think, having talked to some of those guys, I'm not sure they have a lot of that in the back of their minds. I think it's sort of a first step. But it's something that's a necessary step. So no, the plans in that project I've seen don't incorporate, here our objective is to get this much storage into place or to encourage this much penetration of plug-in hybrids and so forth. But they are trying to think ahead. What happens when the first series wave of plug-in hybrids come and we've got, 10,000 people in our service area demanding time of day rates so they can charge at night at, very low electricity rates. So there is that motivator there, but it's not central. Yeah.
These figures, 6-hour charge for 40 mile battery, how does that change throughout the life of that battery and useful life? Is it the beginning or end or average?
Mm-hmm. Well, there's different takes on that. So his question is, how does the battery efficiency and performance change over life? The batteries we're looking at now don't have much of an effect. Over the kinds of lifetimes that you really look at for a car, we're talking about a few percent. You can push them harder than that, but traditionally, batteries are pretty much said to be dead when they're when they've dropped in performance by more than about 20%. So the effects are not that dramatic. The temperature effects are more dramatic. Okay. A car like that is going to perform a lot differently in Champaign in February than in August, and that's a much bigger effect. The energy storage in a typical battery, at roughly the freezing point is perhaps half of what it is at a reasonable room temperature, and that's one of the things they're worried about. Actually, is how do we get proper cold weather performance? And I didn't list that. Maybe I should have, but that's more of a factor than life actually. Certainly in my opinion. Okay, I know there were some other questions too, so I want to wrap it up. One of the things we've heard, I hear this all the time, that various vehicles are quote-unquote stepping stones. So we used to hear that hybrids are a stepping stone to an all-electric car or a fuel cell car or whatever. I don't buy that anymore. I don't think it makes any sense because people buy vehicles because of certain things that they want for personal transportation. And what's inside of it and how it works is a lot more secondary. And granted, all of us have considerations about efficiency and how it impacts our lives and the environment, but how that gets achieved is a little bit different point. And I think the manufacturers now need to face the idea that each one of these different things has its place, and it's a question of how to really make them work out and get them into the market in the right way rather than trying to think of them all as some sort of an intermediate step along some vague pathway. I think the other thing that has become is actually becoming a dilemma is that most of the hybrid vehicles we see on the market today have kind of converged. There's a lot of sameness in the architecture. It turns out that there really aren't a lot of very good reasons for that. And in fact, the ones that we see on the road really don't approach recent history of what is well known to be achievable with electric and indeed even hybrid vehicles. So not only is the jury still out, there's still lots of room for innovation, and it's really important that these guys not get stuck in the wrong directions. So near-term trends, we will see plug-ins quite soon. We may see them quietly enter the market shortly. Certainly the Chevrolet Volt has been trying to make a lot more noise. I actually think it has a fair amount of promise. There are market issues, absolutely, but I think it's got a significant possibility. I think electric vehicle designs will come into play and will be quite viable. Nissan is working on one that they expect to release in about 2 years here that looks really interesting. The emission impacts are large, and indeed they will become larger as we are able to use more renewables, and these kinds of transportation solutions help to implement those. Certainly there's a lot of complementarity there. And when you look, say, compared to biofuels and even petroleum-based resources, there's a lot of very significant advantages here that people haven't been able to take advantage of. So we will see the revival of the electric car. We will see a lot more hybrid cars, and it will make a big difference in the future. And let's take a little bit more time for questions, and I'm sure we need to wrap up. Yeah.
More of a comment than a question. Actually, we're starting an electric vehicle club on campus.
Yeah, that's always a very good question. Safety issues associated with these vehicles. It's actually a lot easier to manage safety, as it turns out, in an electric or hybrid vehicle, well, electric especially, versus trying to manage that 20-gallon box of gasoline. And the Tesla cars, for example, there's some really spectacular pictures from the crash test showing the crush zones and everything else. Fairly easy to package things so that you kind of have a breakaway system. The electronics can respond very quickly, so if problems are detected, you can actually shut the car off before the crash is finished. Very, very limited shock hazard. And in fact, we used to talk to people who were very paranoid about that. They say, "Oh my, you're going to have 300 volts of batteries in this car. You're going to kill people left and right." And I say, "Well, don't you have 300 volts of electricity in your house? You don't seem to mind that." The reason really is because in the auto industry, there's sort of a philosophy that the electrical system is open. The wires are hanging under the dashboard. You can get fingers in them and so forth. Whereas we've said, in an electric or hybrid car, that big battery pack has to be more like a transmission. It's not something you put your fingers into while the car's running. And it needs to be a closed electrical system, like we have in our houses and buildings, so that those kinds of hazards just go away. I mean, it's important to manage them properly. Yeah.
I just wondered, what is the possibility of standardizing the batteries so that you could drive up to a refueling station, pop out your battery, pop in another battery, give them a couple bucks to be on your way?
Right. Yeah, there is in fact a significant startup in Silicon Valley that's working on exactly that kind of model, a standardized battery pack that's interchangeable. And one of the cars I showed had a pack that was designed exactly for that. I think it remains to be seen. One of my colleagues in the electric vehicle industry says, "Okay, now wait a minute. You're telling me you're going to take the most expensive, most energy-intensive element of the car and make it replaceable, and now you're going to have more of them, because obviously you've got to have more battery packs than cars." And he says, that business model is just backwards. I'm not entirely sure I agree with him. But I think that once people have these, they're going to find out that, the long-term charging thing, plug it in the parking meter, plug it in your house, is real easy versus going into a service station and having a battery pack changed out. I think most people now are used to the idea that every now and then you charge your cell phone. It's not that big a deal, but people have to get used to it. Let me get the one in the back here.
So, on the topic of biofuels, it may be likely that they're integrated into these hybrid electric vehicles eventually. Is the conversion efficiency just a linear decrease? So ethanol is about 66% of DBT is gasoline. Would you just lose 66% of your mileage, or is it like more than
Well, the answer is that if you're going to run a hybrid vehicle, sure, use a biofuel, use an alternative fuel. I think the ultimate issue is a much different one, which is, for example, if my objective is to use renewable energy, solar and wind, for example, to power transportation, what's the best way to do that? And it depends. I mean, although the numbers tell you a particular story, the actual needs tell you a different story. Should I convert that energy with solar panels, put it in a battery pack, use a true electric car with a portable energy supply, or should I take that energy, put it into a plant, reconstruct that into a fuel hybrid car? The energy analysis, absolute no-brainer. The solar should go right into the car. But, there's still the range issue. There's still the rate issue. Those don't go away. And if I want to drive my car for 400 miles, it's not happening. So if I want the range, that's got to come from some other resource. Maybe the Chevrolet Volt is the right solution. It's what we call a range extender hybrid. It's a series hybrid. But basically, if I ever buy one, which maybe I will, in Champaign-Urbana, it will probably always be an electric car. But on the other hand, if you want to drive it to Milwaukee, you can put some fuel in it and do it. Maybe if I'm only fueling it twice a year, it doesn't matter what the resource is. So I think it remains to be seen what will really play out. Well, you actually do better because you can, there's no, it's obviously the fuel content is different, but it's very easy to take the engine and say, okay, I'm running ethanol and it's a hybrid car. I'm going to trim this up, in advance because I know what the fuel is to be extremely efficient on this fuel. Everything's matched up for the fuel, and I'm only going to run it when I'm able to use all of that energy as efficiently as possible. And, the driver, whatever the driver asks for, I'll make it up the difference electrically. So, whatever the fuel, you have the opportunity to set up the engine system to get the best possible results from it. So, in that sense, it's a significant benefit. Yeah.
5, 10 years ago, fuel cells were the darling of the industry and stuff like that, and they just seem to have disappeared.
Yeah.
What is besides Bush disappearing, what is the...
Well, reality bites, right? Fuel cells for automobiles are the technology of the future, right? Always have been, always will be. And certainly when those trends came about, and we started looking at that, I think the real key there is there were a lot of people who were relying on sort of the principles of fuel cells being very efficient. It turns out that in automotive sizes, 50% conversion from the ultimate fuel to actual electrical output is a bit optimistic. With a really, really good turbo diesel, small, dedicated to constant operation, you can get 45, 48%. So it turns out to be real incremental. And I think people have finally begun facing up to that. And now so then you say, okay, I want a really nice, efficient fuel cell. Now my fuel is hydrogen. Okay, how am I going to put that on the car? It's not even a question of infrastructure. What kind of a box do I put it in? It opens up a huge can of worms for relatively incremental improvement in efficiency. The objective is still how do I get the full performance of a conventional car with some other undefined benefits that hopefully are positive and measured. Electric car compromises some elements of performance, gives big advantages in other arenas. How do you make that trade-off? The fact is the fuel cell car doesn't give you enough to be very compelling once you get into it deeply. So I hope reality has set in. We'll see. Yeah.
So just to throw a little more technology out there, some of the new engines, like the high-pressure, low-temperature ignition systems and the new transmissions, they say they can improve fuel efficiency by 8% with just the new engine. As if we were running on gasoline. Still, are there plans to integrate those new designs with electric technology? And are they
Yeah.
compatible? It seems like they would be.
Yeah, really good question. There's some very, very nice Volkswagen diesel engines, for example. Extremely efficient, high fuel economy. You can get almost to the levels, and there's fundamental reasons for this. There's no real reason why you couldn't get to that double fuel economy with a somewhat more conventional power plant. But your point's well taken. Can you integrate these then back into a hybrid platform and get even more benefit? And in principle, the answer is yes. And I think maybe that's a way you get to the triple. But once you start wanting to go even beyond that, now you're talking about an electric car. So it becomes a different solution. So the simple answer is yes. I don't know how many projects are going on in those kinds of arenas. I've seen a few. And of course, that old Volvo turbine project was an example. But absolutely, once I build a hybrid plant, I have a lot more possibilities in terms of what I can use for the engine.